Okay, so let's start with problem 8.8. We're told in the information that the quality control manager at a light bulb factory needs to estimate the mean life of a large shipment of light bulbs. So we have an estimation problem, and specifically it's in relation to the mean life of these light bulbs. We're told the standard deviation is 100 hours. A random sample of 64 light bulbs indicates a sample mean life of 350 hours. So we've got some information. At this point, before we even look at the actual Part A question, we know that we're talking about means. Here the application is to the life of light bulbs, but we're specifically talking about means. We've been given some information about the population. We're told the standard deviation is 100 hours. Now notice that information came in the question before we started talking about the sample, and so in this particular context, the standard deviation is in reference to the population. We're then told that for our random sample of 64 light bulbs, we have a sample mean of 350 hours. All the information, we know it's about means, and then we can just look at the actual questions A, B, and C to see what we've got to do with this information. We know it's to do with estimating, that we're estimating something to do with the mean. So that keyword of estimate is a good way to identify that this is a Lecture 8 question. Let's have a look at Part A and see what we've got to do. Construct a 95% confidence interval estimate of the population mean life of light bulbs in the shipment. Now, it's a little bit wordy, but the key thing is that we're wanting to do a 95% confidence interval. We've got a reminder that that's in relation to the mean life of light bulbs, but there really isn't a tricky way to ask you to do a confidence interval. As soon as you see those words, you know that you've got to go and get the formula for your confidence interval and make sure that you use the right formula. It's a good idea to just write down all the information you've been given. You can highlight it as you go through the question, or you can just make a list of it as you go through. We've got our sample mean. We know that X bar is 350. We know the population standard deviation sigma, that's equal to 100. Now just remember that's important because the fact that it's population standard deviation that we have tells us that we'll be using the Z distribution. So remember that when we do anything for means, we have to say to ourselves, do we know sigma or do we not know sigma? And as soon as you've identified that you have sigma, it's always going to be the Z distribution, the normal distribution. We've got our sample size, 64, so we know N. And in Part A, the confidence interval that we want to construct is specifically a 95% confidence interval. Now that's important because we're going to use that in our diagram. So that's going to help us decide what critical values to use. So at this point, we would go across to our formula sheet and see, well, okay, when sigma is known and we're doing a confidence interval for the mean, the formula is X bar plus or minus Z times sigma over the square root of N. Now, don't forget that we always have that same type of format for a confidence interval. It's always the point estimate plus or minus the critical value times standard error. It just so happens that in this problem, because we're talking about the mean, our point estimate will be X bar. Our critical value will be Z. That comes from the fact that we're using the normal distribution. And then the standard error is just sigma over the square root of N. So the real trick with this question is identifying what you're trying to calculate, a confidence interval, the fact that it's a confidence interval for the mean. And once you know you're dealing with means, then a matter of saying is sigma known or is sigma unknown. We've got our formula. Now we can simply substitute in the right values and do the number calculation on the calculator. So our point estimate for the mean is 350. To that, we're adding and subtracting 1.96 times 100 over the square root of 64. Now, the 1.96 comes from the Z diagram. Now, because it's a 95% confidence interval, remember that we put the 95% in the middle of our distribution, in the middle of the Z distribution. If there's 95% in the middle, we've got 5% left over, and therefore 2.5% in either tail. Now, you can use that information to look up 2.5% in the upper tail in your inverse Z table. The value that corresponds to that is 1.96, and of course, because Z is symmetrical, the corresponding value is negative 1.96. But you only need to put in the Z value into the formula, so the 1.96 is really all that you need. That goes into your confidence interval formula, the critical value. You know sigma is 100, you know n is 64. It's really just a matter of doing the number crunching on the calculator. Always work out this adding and subtracting components separately. So do 1.96 times 100 over the square root of 64 first. If you get that as an answer, you can then add it on to 350 as well as subtracting it. So if you work out that component separately, you should get 24.5. Add it on to come up with the upper boundary of 374.5. Subtract it to come up with the lower boundary of 325.5. So there we have our confidence interval, and we've completed part A. Now part A was the practical component. We've got B and C, which just give us a chance to think about, how to interpret this result and really what it's telling us. Now, just keep in mind that part A, we're saying we're 95% confident that the true population mean life of a light bulb. So for the population, we're 95% confident that the mean life of the light bulb is between 325.5 and 374.5 hours. Now, in part B, we're asked whether we think that the manufacturer has the right to state that light bulbs last an average of 400 hours. So, well, what do we think about that? Now, I've got some notes, but let's just talk about it for a moment. If the manufacturer claims that on average the light bulbs last 400 hours, well, we've just finished a confidence interval that says based on the sample we got, we're 95% confident that the true population mean is between 325.5 and 374.5 hours. So 400 hours isn't in the range, and it's actually quite a distance from the range. If we link it back to the sample mean, 400 is 4 standard deviations above the sample mean of 350. So just keep that in mind that, in terms of using this confidence interval we've come up with, yes, when we take a sample, we do expect some sample variation. The sample mean might be a little bit less or a little bit more than the true population mean. Given the data we've been working with, we're 95% confident that the range for the true population mean is between 325.5 and 374.5. So 400 certainly isn't in that range, and because it's so far away from the sample mean, 4 standard deviations, that's very unlikely that we would get a sample mean that far away if the population mean was 400. What about part C? Part C is, must you assume that the population of light bulb life is normally distributed? Well, no. The main thing is that we know our sample size is 64. We've also got sigma, but having a sample size that's 30 or more, we can use the central limit theorem, and it doesn't really matter what the population looks like. As long as our sample size is sufficiently large, we can say that the sampling distribution of the mean, so our X bar distribution, will always be approximately normal because of that larger sample size.